very first time we talked about kinetics, we talked about Newton's second law. So remember, kinetics is all about why things move. We're thinking about forces and masses and things that actually cause motion. Newton's second law, again, sum of the forces equals mass times acceleration. And this is great for purely translational motion, for things just moving in straight lines or very parallel lines. As soon as we start adding rotation, we're going to need a rotational version of this. And conveniently, at least in my mind, it's nearly the same, just with all the rotational components. So in rotation, the equivalent of this that we can use is the sum of the moments, right? Those are forces acting over a distance or over a radius, is the mass moment of inertia I times the angular acceleration alpha. So just term for term, we've gone ahead and taken the linear version of it and put in the rotational version of it. And the textbook has a pretty good derivation of this equation if you want to see the derivation. And so this is sort of our governing equation for this section of the textbook, or for this section of our work. And I'm going to first of all also say that these need to be around the same point. So the sum of the moments about some point A has to equal the mass moment of inertia about that same axis A and the angular acceleration alpha. So a couple things I want to point out here. First, these are vectors. And hopefully in statics, when you talked about moments, you talked about doing moments as vectors. And to solve for the moment vector, you did the radius cross the force. So this is a cross product and the force F. We'll talk about cross products in another video, so look for that somewhere in the same series. And this is our moment calculation. And now I just quickly want to define this. If you have some object, let's just say a random generic wheel that's rotating about, let's just go ahead and say its center, we, as a vector, some angular acceleration alpha, so this alpha in particular, will be in the negative k hat direction. If I have my I and j's in the normal direction and k is kind of coming out of the board at us. This is my ijk. So these vectors are always, I think of them as going through the axis of rotation, so they'll be in and out of the board straight through that rotational axis. And then we can always use the right-hand rule to identify whether it's positive or negative. So the way you do your right-hand rule is you make your fingers curl in the direction of motion. So in this case, if I have it going that way, my fingers curl. And if you stick your thumb out, it'll point in the direction of that vector. So in this case, my thumb is pointing straight into the board, which was again a negative k hat. So in the other direction, this alpha will be in the positive k hat direction. If I make my fingers go in the direction of motion, which is this way, curling around, my thumb is in that direction of that vector, which is the k hat direction, the positive k hat direction out of the board. If you cannot for your life remember which is your left or your right hand, or you can't make these work, you can always remember that counterclockwise, I guess, is positive. Counterclockwise is positive, and clockwise is negative. And that will always be true as well. So you could also always remember counterclockwise is positive, clockwise is negative. That's our governing theory here. And we could also imagine that we might be able to combine this with our sum of the forces equals mass times acceleration, our actual Newton's second law, to figure out a lot of information about motion. And that's what we're going to be doing in this section here.